Hello everyone, thank you for joining in today. My name is Joseph Celestine Donald and I'm a certified SOLIDWORks expert and I'm a SOLIDWORks champion, right? And also I'm a certified SOLIDWORks simulation professional. Now today we'll be talking about an argument, it's sort of an argument that I myself and my colleague had, right? We were discussion and the argument came between a welded joint and a bolt joint, which would actually last. Right now the question was actually longevity, but for starters I said okay, when I'm trying to validate, I'm gonna go with slower and then faster, right? So I'm gonna go with the basic, which would fail first. What we're gonna do is this: we are going to apply a certain material, we're going to apply a certain load, and then we're going to watch them fail and see which would actually fail the most, at how they would react to two scenarios. Two scenarios separately. First scenario would be when we apply a force of 10,000 Newton, and then the second scenario would be when we increase the force, escalate it to 90,000 and see what reaction we get, right? Now, like I've said in my previous videos, FEA simulations are basically straightforward. You get your geometry, you got your material, geometry, material, fixtures, load, and then you mesh, and then you run your design, your simulation. It's that basic, right? Now let's talk. When we talk about let's see scenario one. We'll talk about the loading conditions itself. Sorry, when we talk about the geometry is pretty straightforward for the weldment. It's built with weldment, of course, but it's straightforward because here we just use since we'll be using bolts, so we simulated them as separate parts and then assemble them together. And then what is quite important is the end plates. The end plates, it's if you check evaluate and you check measure, you see that the end plate, it's a 11.3, right? 11.3 thick end plate that actually holds, right? Good. Then when we talk about material selection, we used the STM A36 steel, right? In my previous video, if you've not watched it, just check it out. I actually explained what it actually means, but I'm going to reiterate just the important part, which is the A36, which actually basically means that your design, the material would actually has a yield strength of about 36 it's a kilopascal per inch or something, but when you convert it, it's approximately 250 megapascal, right? So when I say what's the fail point, the yield point of this material before it begins to fail, it's 250 megapascals, right? Now, good. So let's jump straight to simulation, right? Now, simulating the bolts itself, the bolted scenario, it's not really complex, right? Like I said, your first step would be to select your geometry. We've already done the geometry. Make sure it's probably done. Good. And then next we'd move to actual let's skip the connection part. I'm going to come back to it back. Then we'll talk about materials. We've already applied materials. Then fixtures. Now we want to mimic it actually standing still. We don't want to fix the back, because when we fix the back, it actually acts as if it is actually built into the wall. We want to see how it actually reacts. This actually reacts when it's pulled, when it's just fixed on the top and it's standing, right? Let's say a column a beam in a bridge, or you understand my point, right? Good. So then force, we are applying a force of 10,000 Newton, which should be equivalent to, I think, a car or a car. It wouldn't be as big as a bus, but it should be around that range. Okay, 10,000. Select your face where you want the force to be applied. I don't want it to be applied here. I want it to be applied here. Well, when you're doing your simulation, I will include the CAD files in the description, so when you're doing your simulation, you can actually mess around wherever you want. You can apply the forces here and here, wherever you want to apply the forces, right? Good. Force. And then let's talk connections, right? We have two options. Now, at default, when you import an assembly file into SolidWorks, right, it assumes they are bonded, and we don't want them to act like as if they are from one carved part, right? We want it to show that we are bolting them together, right? That's very, very important, right? So the first thing I did was to go to the component, the default interaction, which is the global interaction, which is bonded mesh, and I suppress it, right? Good. And then I apply. This is where it actually, when it comes to connection, differs from the welded scenario. So pay attention. Now for the component, I suppressed it, and then I attached a local interaction contact. For the local interaction, I made sure just these two parts that are touching contacts, right? If you want to understand, if you want to apply this, like, it's face to the back, so it's very difficult to actually get the back, right? What you do is you right click. You would see an option if you're in the design tree. Look through the design tree. When you want to select, right, let's say you want to select this edge, you right click, you would see select others. It gives you the option of selecting the faces that you've not selected, right? So you want, obviously this face I've already selected won't pop up, but when you have not, it shows for you. Okay, good. Now we've talked about the bondings themselves to mimic real life, right? They are in contact, they are not bonded. Then we make a very, 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 very important input here. This is because now for the bolts themselves, I didn't use physical bolts, because the physical bolts would actually increase the mesh time, and we would not actually get what we actually want. Now the physical bolt would actually act just like a placeholder. It wouldn't actually mimic, it would be there passive and just makes the design complex. We want the bolts themselves to be actually present, but not just present. We want the bolts to actually function. Now when you attach bolts in real life, right, you get there is an amount of torque applied to said bolts, right? Like when you tighten it, even before you apply any load, before you apply any force, you apply anything, a force is already acting on it when you tighten it, right? You go to your connection, you select your bolts and your bolts rather, you select it. Now I'm going to show you, these are the bolts. You have to select them one by one. It takes a bit of time, but what I want to iterate here is, okay, now when you select your bolts, you select the beginning edge where you want to start from, and then you select the end edge. It's very important you don't mix it up. Good. And then the diameter takes the diameter of the hole at default, and then it extends to give you the hexagonal edge of the top of the bolts themselves. So of course it's going to be bigger. You cannot tie it, but you can just leave it as default. Then this is what I'm talking about. We're applying the force. At default, the force we could apply would be, I would recommend this 150, but I thought how massive this looks, and so I went for 200 torque. So this is basically the tightening force applied on it as it's pressing the plates, as it presses the face, our outer face to this of the column to this beam, right? Now we've done that, and then we right click and we create mesh. Now on my previous video I explained what mesh is. Mesh is basically you splitting your model into multiple parts, right? And you see where it actually tightens spots where it actually concentrates on. So I'm going to do a separate video on stress on meshes. Okay, good. Now we right click and you can run here, or you can just go to the top, right click, and then you see run simulation, right? Good. Now we're not going to run because it's going to take a bit of time, so I'm just going to jump into the results. Now for the results, your result don't appear this way at default. They have a default appearance, more scientific. So what you do is you right click, you check, and you make sure they are translated in a way you understand. Is preference based, right? For me, I just straight up I want to see the megapascal, it's in megapascal, because I want to see my stress. I use strength in megapascal, and then I want to see my failure in megapascal. When I go to chart options, I can show the maximum force and the maximum stress and the minimum stress and where they actually occurs, right? Like I said, now this, like I said, the values here, they come scientific, so it's a bit tricky to understand. So you can just convert to floating, and then you can actually just do your okay, right? So if I say okay, then your decimal place, of course you can alter it, but that's just your choice. Now it's very important to say that for this our first scenario, we get a maximum stress of 34.38, approximately almost 35, right? Which is very, very safe, right? It's negligible. There's no really, I mean, we have a yield strength of 250 and we're getting a stress of 34 right, 0.3. So the material is safe, right? Now when you confirm with your displacement rather, it tells you how deformed it is, and then of course you do the same thing to actually give you appropriate display to get what you actually want, like select the maximum and all that. But it's very important to notice like that for your displacement, you get a displacement that's less than 1, right? Now whilst the displacement really wouldn't matter, because you just want to know if it fails, right? Because of how the material is, it might not be malleable enough, or it might not heal enough before it actually breaks, but the deformation actually helps you seal how it will actually perform. Now for instance, if I right click and I actually escalate the deformation, like I want to see how, like I want to user define, I want to put let's say 30, let's see how 30 looks like, and I say okay. When I animate the deformation, you see that there's now some sort of like movement. You see how it actually reacts, right? Good. So for the stress, you can also animate to see how the stress is actually transferred, right? Good. Now the question that comes, it's safe, right? But how safe? That's where the factor of safety plot comes in. It doesn't come as default. You right click and you select your factor of safety plot. Okay, now your factor of safety plot tells you how safe is your material, right? For this our simulation, our factor of safety is 7.3, right? It tells you that your material is 7, it will take 7 times the force being applied on it at the moment to actually fail, right? That's what factor of safety basically tells you. Of course you can edit the chart and just check these values yourself, but that's what our factor of safety says. So it tells you your material is safe, right? We're going to compare the stress, the displacement, and the factor of safety, and compare it to the other scenario. Right now let's talk about the other scenario, which is the welded scenario 2. Now scenario 2, the basic things are very quite important. Like I said, geometry, which is important. Material geometry would be welded, just mated to the face. We've gotten geometry. Now material, which is ASTM, we've gotten that. 836, we've gotten that. And then we go for fixtures. I'm going to ignore the connections now and then come back to it again as we did before. Then fixtures, it's fixed the same way we want it to be fixed. External load applying 10,000 newtons, so we get a comparable answer. Good. And then now we'll talk about the connection. Stay with me, which is actually one of the most important parts, like I said. Now for the connection, you have to pay attention, because the interactions, remember before there was a global connection which was actually bonded at default, like I said, which we suppressed. But here we don't suppress, we turn the global connection to contact, which tells you that okay, at default it touches, it is not carved from the same, the global connection, it's not carved from the same wood, right? It is touching contact. But then when we apply our local interaction, we apply bonded, which tells you it is welded, right? Now another way of getting that weldment would be actually edge weld. right click your edge weld, and then you select the edge. But it actually really needs what it needs is you to actually now get the external. You'd have to now create your external what's it called, you like I explained before. I will now be having the options of, because when you try to now mesh, it's kind of like, since we're not trying to pay attention to the stress exactly at that point, right? We're not trying to check the stress for the weld beads themselves, since we couldn't like mold do extrude boss base for the weld beads, mate them there, which is going to take a lot of time, and then when it comes to meshing, it's going to make it a bit difficult. Okay, good. Now straightforward, we go to meshing directly. When we mesh instantly, and then we run our studies, right? When you check your stress, we get the stress value of 43.37, which is higher than the 3.8, no, is it 3.8, 3.53, the noted 5.3, which we got for our previous bolted, right? So it tells you your maximum stress is this, right? Of course, you can now change and alter whatever it is you want to alter here to suit your personal need, right? Good. So then let's look displacement. Displacement is 0.13. Previously was 0.12, right? So it's not much. So now we know the material is safe, but the question now comes, how safe is it? Now that's when we now come to factor of safety. Factor of safety here is 5.8. Now before, our previous factor of safety was 7.3, and now we get the factor of safety was 5.8. So it tells you 5.8. It will take 5.8 times the amount of force being applied right now to actually get it to fill. Okay, good. So now let's escalate the whole thing, right? Let's apply a force of a load or a force of 90,000 Newton, like I said in the beginning. Now for 90,000 Newton, the whole setup is actually the same, of course. The only difference is the force per item that we actually put, the force itself, which changes to 90,000, and then we check our vomit stress. And when we check our stress, of course, if you're doing it, you'd have to run again to get an appropriate answer, right? Now to get its stress, now our maximum stress is 388. It fails, right? Our use strength is 250. If here our maximum tensor stress here is 388, it tells you it fails. Okay, it tells you it fails, and then when you zoom in, you can see where it actually fails. Then when we check the deformation, I'm gonna try and I'm gonna escalate I'm gonna scale up the deformation so it's visible. I'm gonna say let's scale up to like 50. Okay, now the deformation, the plasticity depends on the material, right? It depends on the material, but it tells you that it actually fails. Okay, now if I try to animate, you see it actually fails. Okay, now of course SolidWorks won't actually show you it pulling out. Of course it won't show you it pulling out, but you now, ordinary engineers look at the colors and the fancy gradients, but as an engineer you look at the numbers. What does the number say? The number says it fails, and then it fails, right? And then we now say to confirm how does it feel, we then check our factor of safety. Our factor of safety basically tells us it's 0.62, and what 0.62 basically means is that it's less than 1. At default, any product out there should have a factor of safety of at least 2, right? So most people even raise it to 3. Depends on how critical the part is. For aerodynamic parts, the factor of safety goes as high as 7, because there's high extreme temperature and high environment, right? Factors that actually play into it. So you don't want to go let's say your brake is built has a factor of safety of exactly 1, right? And the force applied you can apply on it is 500, right? And then one day you're moving and you almost hit the cut, and you want to try your best and just dodge, and then you mistakenly you like panic and you exert the force above 500, and then it just breaks. That's going to be catastrophic. So when next time you hit your brake, you understand that someone actually thought and said, okay, the factor of safety should be more than 1, or at least should be more than 2, depending on the size, because people's strength varies. So there's going to be a study done, and it's going to be a safe bet. and a safe limit for it. Okay, then when we run the simulation on the on for 9,000 on the bolted section, basically the same thing, right? But the only difference is the force per item. And then when we check the stress, you see we now have a stress value of 258.2. So it's basically almost escaped, but it actually failed, right? So when it comes to comparison of failure, it failed, right? So there is no now the only thing that would vary now at this point would be what force would it fail. The force it would fail would be different, right? For instance, for the bolted section, now we can actually reduce the force to get, we can actually see now to get the weld to actually fade. Now you can actually, for the welded one, now you can reduce the force and at least dial it back a little bit and it would still fail. So in retrospect, what I'm trying to say is this: the number says that the bolted one performs better, right? When we check the displacement, it has a displacement of 0.1 point, right? Of course, but the factor of safety tells you that it is 0.95, which is a better, I think, compared, which is better compared to, let's see, yeah, which is better compared to for scenario, yes, we get 9.9, which is actually way better than when it's welded, which is actually 0.6, right? But when in retrospect, like I've already said, 2, right? 2 is a safe. So if it's not 2, it actually failed. Okay. Now, the conclusion I drew from this whole study and the whole simulation is that, well, the reason why, when you again ask the question, why did it perform better? Why did the simulation, why did the boat perform better? You could easily say the reason it performed better was because of the plate there, right? The 11.3 plates that was there, so the stress was able to distribute around the plate before it actually hit the beam. So that was why it actually performed better. Then, but at a pure stiffness standpoint, you actually have to understand that both failed and both worked, right? So even when you compare them, like, of course, when you compare them, you see that there's a difference, but they both actually failed and they both actually worked. So realistically speaking, each could go. The preference right now would now be things like longevity, ease of assembly, manufacturability, cost, bolts, replacing the bolts and washers every time. So those factors now play into your selection, but at the end of the day, it doesn't really, the simulation for this first right concludes that they are actually the same. Now, when we want to further it, would now go checking the stress that actually happens in the bead, right? In the stress bead, in the weld beads themselves. Okay. Thank you very much for staying to the end. As usual, my LinkedIn link would be on the bio. You can reach out to me and I will try my best to answer any question you have. You should also comment your questions on that and I check it and I can reply so everyone can actually learn. Thank you very much. Thank you. All right. See you. If you've not subscribed, please try and subscribe and I'll see you in the next video.